How do Dunkin, Chick-fil-A, and McDonald's pump out millions of orders a day without everything breaking down into total chaos? In this video, we go behind the scenes of their kitchens and supply chains, revealing the prep methods, timing tricks, and high-speed processes that keep donuts frying and burgers moving non-stop. A high-volume Dunkin' Donuts line is built around delivering dough or batter to hot oil in the same condition every minute, because frying fixes shape, crumb, and surface in seconds and leaves little opportunity to correct variation downstream. Ingredient conditioning starts the process. Flour is sieved to remove lumps and aerated for consistent hydration. Sugar is screened so crystal size stays stable and dissolves predictably in mixers. Salt and leavening are pre-blended, so distribution is uniform at low inclusion rates. Fats are tempered so their plasticity is consistent for dough systems, or melted and cooled to a target temperature for batter systems. Eggs and dairy liquids are tempered because small temperature shifts change emulsion behavior and batter viscosity. Water temperature is selected to land the final dough or batter in a narrow temperature window. For yeast-raised donuts, the front end is a developed dough that must proof consistently. Flour enters a mixer and is hydrated with water and dairy liquids, while yeast is dispersed early, so fermentation is uniform. Mixing begins slowly to hydrate without dusting, then increases speed to develop gluten. Gluten development is tuned to a target elasticity that can trap gas but still sheet cleanly. Fat is added after initial gluten formation, so it softens the network without blocking development. Eggs and emulsifiers are incorporated in a controlled sequence, so they form a stable dispersion inside the dough rather than separating into streaks. Dough temperature is managed as a primary control variable. Mixing friction generates heat, so water temperature and mix time are adjusted to reach a target dough exit temperature. That exit temperature controls dough stiffness and yeast activity. The dough then enters a timed rest, where moisture equalizes and gluten relaxes. Relaxation reduces snapback in sheeting and improves cut accuracy, while early fermentation begins creating fine gas cells without fully expanding the dough. The rested dough feeds a divider and sheeter. Dividing stabilizes feed rate into rollers, so thickness remains steady across time. Sheeting reduces thickness through several roller gaps rather than one large reduction to avoid stress lines that later become weak points in the fryer. Gauge rollers lock the final sheet thickness, which becomes a main determinant of donut weight and final crumb thickness. Rotary cutters punch rings at line speed, cutting an outer diameter and removing the center plug. Cutter sharpness matters because dull edges compress the dough and create ragged rims that absorb more oil and brown unevenly. Scrap around the cutouts is lifted and returned to the dough stream at controlled ratios, because high scrap ratios increase working and shift gluten development. Cut rings move into proofing, where the dough expands to near final volume. Proofing is run at controlled temperature and humidity. Temperature sets yeast gas production rate, and humidity prevents a dry skin that would restrict expansion and cause blowouts. Proof time is tuned to reach a target volume and cell structure. Underproof yields dense donuts with limited lift. Overproof yields fragile donuts that collapse when moved or flipped in oil. For cake-style donuts, the line works with a chemically leavened batter rather than a fermented dough, so the objective is minimal gluten with uniform leavening dispersion. Dry ingredients are pre-blended, so chemical leavening and salt are evenly distributed. Liquid ingredients are blended separately, so eggs and fats emulsify before meeting flour. The streams combine and mix only long enough to hydrate flour and remove lumps, because overmixing develops gluten and produces tough donuts with irregular cracking. Batter temperature is held tightly because viscosity must remain stable for depositing. If batter is too thin, it spreads and loses ring definition when it hits oil. If too thick, it deposits unevenly and can trap air pockets that create voids. Depositing forms rings directly into the fryer for cake products. A depositor meters batter through shaped nozzles with timing synchronized to the fryer conveyor, so spacing is consistent. Deposit weight is controlled by pump stroke or timed flow. The batter must release cleanly from the nozzle and hold its shape long enough for the surface to set in oil. Frying is the setting step for both routes. Oil temperature, dwell time, and turnover are the controlling variables. When a donut enters oil, surface water flashes to steam, creating outward pressure that expands the structure and delays oil penetration during the earliest phase. Starch gelatinizes at the surface and forms a crust. Proteins coagulate and lock the structure. Browning reactions accelerate as the surface dries, creating the final color and flavor profile of the crust. Yeast-raised rings usually float and fry on one side first. Conveyor speed determines how long the first side sets before a turning mechanism flips the donut. Flip timing is critical. Flipping too early deforms the ring and creates flat spots. Flipping too late creates an overly thick crust on one side and uneven color. The second side fry completes structure set and balances moisture loss so the donut does not warp. Cake donuts set more quickly because the batter begins as a suspension with chemical gas release and rapid heat penetration. Fry conditions are tuned so the surface sets at the right moment. If the surface sets too fast, expanding gases crack the crust and create blowouts. If the surface sets too slowly, the batter spreads and forms misshapes. Residence time and temperature are adjusted together to manage this balance. Oil management runs continuously because crumb fragments and batter fines burn and darken the oil, changing heat, transfer, and color development. Filtration removes fines and keeps the oil clean. Oil is circulated to maintain uniform temperature across the fryer width and prevent striping. Controlled oil turnover keeps frying behavior stable, so the same dwell time produces the same color and oil pickup. As donuts exit the fryer, surface oil is removed immediately. Drain belts and vibrating conveyors shake off free oil, and air blowers strip oil from creases. This step is important because surface oil interferes with glaze adhesion and increases greasy feel. The donuts then enter cooling, where internal steam condenses, fats begin to crystallize, and the crumb firms. Cooling is staged to stabilize structure and prepare for finishing. Hot donuts are soft because fats are liquid and the crust is still plastic. As they cool, the crust becomes rigid and the interior moisture redistributes. Cooling airflow is controlled so the surface does not dry too fast, which would create a tough crust that flakes under glaze. Cooling also prevents packing too warm, because warm donuts release moisture into packages and soften coatings. Glazing and icing are applied in controlled viscosity windows. A classic sugar glaze is mixed to a defined solids level and held warm enough to flow as a thin film. Donuts pass under a glaze curtain or are dipped, and the excess drains as they travel on a setting conveyor. As water evaporates, the glaze crystallizes into a smooth shell. Chocolate or fat-based icings are heated to a target flow temperature and applied by curtain or dipping, then set by cooling so the fat network solidifies without cracking. Powdered sugar or cinnamon sugar finishes are applied while the donut surface still has slight warmth and tack. The donuts pass through a shower or drum that distributes powder evenly, and screens recover excess. Toppings are applied during the short tack window before coating set. Feeders meter sprinkles or nut pieces at a rate synchronized to belt speed, so coverage stays uniform without clumps. Filled donuts at an injection step after cooling reaches a firm but pliable state. Fillings are prepared to a pumpable viscosity that holds shape without leaking. Multi-needle injectors penetrate at controlled depth and piston strokes deliver consistent doses. Needle retraction timing is coordinated to reduce backflow and surface smearing. If a side fill format is used, a controlled slit is cut, and a nozzle deposits filling into the pocket. Then the product passes through a brief set zone so the filling surface stabilizes. Packaging is designed around protecting finishes and managing moisture exchange. Donuts intended to stay soft use barrier materials that reduce moisture loss. Donuts with a crisp shell need packs that prevent moisture gain that would soften crust and glaze. Cartons and clamshells protect toppings from abrasion and reduce contact marks, while flow wrap provides strong moisture control but requires the surface to be fully set to avoid smearing. Seal temperature and dwell are tuned so seals close without heating the donut enough to soften coatings. A Chick-fil-A style breaded chicken fillet is produced by turning trimmed poultry breast into uniform portions, conditioning the meat so it stays juicy after cooking, applying a controlled flour and batter system that bonds tightly, setting the coating quickly in hot oil, then chilling and packaging so every fillet reheats with the same crust and bite. Production starts with raw poultry arriving chilled and moving into size reduction and standardization. Breast meat is trimmed to remove thin tails and ragged edges that would overcook and create hard spots. The trimmed pieces are sorted by weight band so the forming line can hold a tight portion range. Consistent portion mass is a core control because fry time and internal temperature rise rate depend on thickness. The meat is then conditioned to stabilize moisture, retention, and texture. A measured solution is prepared from water, salt, and functional ingredients that improve binding and reduce purge. This solution is mixed to a defined concentration and held cold so it does not warm the meat. The solution is introduced to the meat by tumbling or by injection followed by tumbling. Tumbling cycles alternate between rotation and rest so the solution distributes through muscle fibers without tearing them. Vacuum tumbling is often used because removing trapped air improves uptake consistency and reduces voids that can appear as soft pockets after cooking. The endpoint is judged by pickup percentage and by uniform surface tack rather than by extended mixing time. Once conditioned, the meat is portioned into fillet shapes. If whole muscle fillets are used, they are pressed to a consistent thickness using calibrated rollers. Pressing is gentle and aims to widen and even the piece without shredding. Thickness control matters because a thick center can remain undercooked when the crust looks done. If formed fillets are used, the meat is ground coarsely and then shaped in a forming machine. But a classic sandwich fillet format typically relies on whole muscle thickness control rather than full comminution. After shaping, the fillets pass through a brief chill stage. Chilling firms the surface proteins and improves handling so the pieces do not smear when they enter the coating system. Chilling also stabilizes the pickup behavior of the next layers because warmer surfaces thin the batter and increase coating variability. The coating system is built as a multi-step adhesion stack. The first layer is a pre-dust, usually a seasoned flour blend that absorbs surface moisture and creates a dry interface. Pre-dust is delivered as a curtain or bed where fillets tumble and roll so all surfaces are covered. Excess pre-dust is removed by gentle shaking because too much dry flour creates thick patches that later detach. After pre-dust, the fillets enter a batter stage. The batter is mixed in tanks that maintain solid suspension and viscosity. Viscosity is monitored because it determines coating thickness and how the batter bridges surface contours. Batter temperature is controlled because warm batter flows too thin and produces weak coating, while cold batter thickens and creates ridges. The fillets pass through a batter waterfall or immersion where every surface is wetted. Air knives can remove excess and set a uniform film thickness. Breading follows immediately while the batter is still wet. breading is usually a seasoned flour system with a defined particle size distribution. Some formats use a mix of fine flour and larger crumb to create a textured crust. The fillets travel through a bed of breading, while top belts press lightly to embed particles. This compression step is critical because it turns loose surface flour into a mechanically locked layer that will survive frying and later handling. Excess breading is removed so the crust is thick but not clumpy. If the target crust requires a distinctive craggy surface, the line can use a second batter and breading pass. The first pass builds the base, and the second pass builds height and texture. Each pass is tuned, so the coating does not become so heavy that it insulates the meat and slows cooking. After breading, the fillets enter a short setting zone before frying. This can be a brief rest on a belt that allows the batter to hydrate the dry breading and form a cohesive paste at the interface. Hydration improves adhesion and reduces blow-off in the fryer. The rest time is short because the coating must not become wet enough to smear. Frying is the structure setting step. Fillets enter a continuous fryer where oil temperature and dwell time are tightly controlled. The fillets are held under oil by a top belt so they cook evenly and do not float and curl. As the fillet enters oil, surface water flashes to steam. That steam creates outward pressure that expands the coating slightly and forms pores. Starches in the batter gelatinize and then begin to dry into a rigid network. Proteins in the batter coagulate and lock the crust shape. Oil temperature is chosen to set the crust quickly while allowing heat to penetrate the meat at a controlled rate. If oil is too hot, the crust darkens before the center reaches the target internal temperature. If oil is too cool, the crust sets slowly, absorbs more oil, and becomes heavy. Dwell time is set by belt speed and fryer length. Bed loading is controlled because overcrowding reduces oil circulation and causes uneven color. Oil management runs continuously because breading fragments break off and will burn if not removed. Filtration systems remove fines and keep the oil clean. Circulation keeps temperature uniform across the fryer width. Fresh oil makeup maintains quality so heat transfer and browning stay consistent. At fryer exit, surface oil is removed by vibration and air stripping. Removing surface oil reduces greasiness and improves how the fillets package and reheat. The fillets then enter a cooling stage. Cooling stabilizes the crust and lets internal steam pressure fall gradually. If cooling is too fast, the crust can contract and separate slightly. If cooling is too slow, residual heat can soften the coating and reduce crispness. From here, the process can diverge depending on distribution format. For a chilled product, the fillets are cooled rapidly to a target core temperature and held under controlled conditions. For a frozen product, the fillets enter an individual quick freezer. The freezer uses high-velocity cold air to freeze quickly and preserve crust porosity. Rapid freezing forms smaller ice crystals and reduces moisture migration that would soften the crust later. The pieces are spaced so they freeze individually and do not stick. After freezing, the fillets are screened and inspected. Broken coating fragments are removed because they increase crumbs in the package and can burn during reheating. Size and weight checks confirm portion control. Optical systems can reject misshapes and incomplete coating. Metal detection can be placed after freezing when product flow is stable. Packaging begins with portioning. Multi-head weighers or counting systems assemble target weights for bags or cases. Drop heights are minimized because frozen breading can chip and create fines. Bags are formed from barrier film that limits moisture exchange. Moisture control is crucial because the crust will lose crisp potential if it picks up moisture in storage. Seals are made with controlled heat so the film closes without wrinkles. Seal areas must remain clean because crumbs can interfere with seal integrity. For food service formats, the fillets are packed into lined cases with internal bags. Case fill patterns are chosen to reduce compression on lower layers. Cases are sealed and coated. Pallet stacking is designed to avoid crushing that would fracture crust. Storage temperature stability prevents freeze-thaw cycles that create ice crystals on the crust and degrade reheating performance. The final product performance is engineered into the factory steps. Meat conditioning sets moisture retention, so the fillet stays juicy after a high heat finish. Pre-dust and batter create a bonded interface, so the crust does not slide off when bitten. Breading particle size and compression set the surface texture. Fry temperature sets pore structure and crust rigidity. Cooling and freezing preserve that structure. Packaging maintains low moisture exchange, so the crust can crisp again during final cooking or reheating. A McDonald's-style hamburger is manufactured by turning beef trim into uniform patties that cook the same way every time, producing buns that stay soft yet resilient after freezing and toasting, then portioning and packaging each component so it can be assembled rapidly with consistent texture. Beef patty production starts with raw trim selection and temperature control because fat level and grind behavior determine bite and shrink. Beef arrives as chilled trim in defined lean to fat bands. The trim is inspected for hard connective pieces that would create tough spots and for excessive surface fat that would smear during grinding. Trim is kept cold from the start because warm fat smears into a paste, which causes dense patties and poor cook texture. The trim enters a coarse grinding stage first. Coarse grinding breaks the meat into uniform chunks without turning it into an emulsion. This is done through a grinder plate with larger holes, so particle definition is preserved. The coarse ground meat then moves to blending, where multiple trim lots are combined to hit a target fat percentage. Blending uses paddles that fold the meat rather than whip it, because air incorporation and overworking change density and can create voids. After blending, the meat is ground again through a finer plate to create the target particle size distribution. Particle size affects how the patty binds and how it releases juices. Too coarse yields a crumbly patty that breaks at the edges. Too fine yields a tight, rubbery bite. Grind temperature is monitored continuously because friction can warm the meat. If temperature rises, the line slows or adds colder meat to keep the mix in range. The blended grind is moved quickly to forming. Forming turns the loose ground meat into patties with a fixed diameter, thickness, and mass. A patty former meters meat into a cavity and compresses it to a set density. Compression must be strong enough to make the patty hold together during freezing and handling. Compression must not be so strong that the patty becomes dense and loses its characteristic bite. Formers often imprint a pattern on the surface. The imprint increases surface area and helps heat penetrate evenly during cooking. Weight control is enforced at the forming head. Portioning is measured by volume with density control or by mass flow with feedback. Tight weight control is important because cook time is fixed in high volume systems, so patties must reach target internal temperature within the same dwell. Patty thickness control is equally critical because a thicker patty heats slower and will be underdone when a thinner one is correct. Immediately after forming, patties enter a rapid freezing step. Freezing locks the shape and prevents patties from sticking together. Individual quick freezing is used with high velocity cold air. The patties travel on a belt through a tunnel where cold air freezes the surface quickly first, then drives the core down to the target temperature. Rapid freezing forms smaller ice crystals and preserves texture better than slow freezing, which can create larger crystals that damage muscle structure. Patties are then separated, counted, and stacked into interleaved layers. Interleaving uses paper or film sheets between patties to prevent adhesion and simplify later separation. Stacking pressure is controlled so patties do not deform. The stacks are bagged or boxed in a way that limits moisture exchange and protects edges from chipping. Metal detection and weight verification typically occur after freezing when product flow is stable and consistent. The bun is produced on a separate bakery line, built around controlling softness, resilience, and freeze-thaw stability. Flour is sieved and blended to a target protein range because gluten strength controls how the bun holds up to toasting and compression. Sugar and salt are metered precisely. Yeast is staged as a controlled addition because fermentation rate must match line speed. Fats and emulsifiers are included to soften crumb and extend softness after freezing. Water temperature is controlled because dough temperature drives fermentation speed and dough handling. Mixing develops gluten to a defined endpoint. The dough must be strong enough to trap gas and rise, but not so strong that the bun becomes chewy or tough. Mixing begins with hydration and then transitions into higher energy kneading until the dough reaches a smooth, elastic state. Dough temperature is checked at discharge because mixer friction can warm the dough and accelerate fermentation. If dough exits too warm, proof times shorten and the process becomes unstable. After mixing, dough is rested and then divided. Dividers. Portion dough into equal pieces by weight. Portion weight directly determines bun diameter and height. Divided pieces are rounded to create surface tension, which supports a uniform shape during proofing. Rounded dough balls then rest briefly to relax so they can be shaped without tearing. Shaping forms the final bun geometry. Dough balls are flattened slightly and placed onto baking trays or oven bands. Proofing follows in a warm, humid environment. Proof temperature controls yeast activity and gas generation. Humidity prevents skin formation so the bun can expand smoothly. Proof time is tuned so buns reach a target volume and internal cell structure. Underproof yields dense buns with low softness. Overproof yields weak buns that collapse and wrinkle. Baking sets structure and dries the bun to a controlled moisture endpoint. Tunnel ovens run zoned heat so the surface sets and the crumb cooks without excessive crust hardness. Early oven zones drive oven spring as trapped gas expands. Mid zones gelatinize starch and coagulate proteins to fix the crumb. Later zones develop a light crust color and finish internal moisture reduction. The bun must not be too dry because it will feel stale. It must not be too wet because it will collapse and compress poorly. After baking, buns cool on conveyors with controlled airflow. Cooling sets the crumb as fats crystallize and moisture redistributes. Slicing is done after cooling reaches the right firmness. Slicers cut buns horizontally with blades that maintain a consistent hinge or full separation depending on format. Slice depth is controlled because it affects later toasting behavior and bun strength during assembly. Sesame seeding, if used, is applied either before baking for adhesion or after with an adhesive wash depending on equipment design. For high volume distribution, buns are often frozen. Freezing protects softness and allows stable inventory. Buns enter a freezing tunnel where surface is frozen quickly to maintain shape. Packaging then seals buns in bags with barrier properties that limit dehydration. Bag seals must be strong because freezer burn dries bun surfaces and changes toasting behavior. Cheese slices, pickles, onions, and sauces are produced as separate streams with their own controls. But in the context of assembly readiness, the main requirement is portion uniformity and stable handling. Cheese is portioned into slices with tight thickness. Pickles are cut to consistent thickness, so acidity and crunch are predictable per unit. Dehydrated onions are produced by slicing onions and drying them to a low moisture level, then sizing flakes, so rehydration in the final product is consistent. Sauces are mixed as emulsions with defined viscosity, so dispensing systems deliver repeatable weights. Packaging and logistics are treated as part of the production system because the end product depends on thaw and cook behavior. Frozen patties are boxed in counts that match downstream loading systems. Boxes are designed to stack without crushing product. Buns are packaged to reduce moisture loss and protect shape. Temperature stability through storage is critical because freeze-thaw cycles create ice crystals that damage texture and cause condensation inside packs. The final operational transformation happens at the cooking line, where frozen patties are separated and cooked on a clamshell grill. The clamshell grill is engineered for repeatability. Patties are loaded onto a lower hot platen, and then a top platen closes to contact both sides. Contact cooking on both sides reduces cook time and ensures uniform heat penetration. Time and platen temperature are fixed, which is why patty thickness and mass upstream must be consistent. The surface imprint on the patty increases contact and helps fat render evenly. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees Celsius to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in two stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300-500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60-80 degrees Celsius, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees AS to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50-55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System, and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders, and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 C, 160 C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase for the final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system, a stainless steel planetary mixer, or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low-shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps, monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high-shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture. invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree bricks, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired bricks and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed inline or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 degrees Celsius. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Labeled jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability. Dr. Pepper production begins with water purification. Incoming municipal water is first passed through a series of coarse filters to remove sediment and particulates. It then flows into a multi-stage filtration system, including activated carbon beds that strip away chlorine, organic compounds, and any residual taste or odor. The water is then softened through ion exchange columns that extract calcium and magnesium. Finally, the water passes through reverse osmosis membranes operating at high pressure, forcing the liquid through semi-permeable membranes that eliminate dissolved solids, heavy metals, and microorganisms. The purified water is collected in stainless steel holding tanks, agitated continuously to maintain consistency and prevent stagnation. Concurrently, concentrated syrup production begins. This involves a precise blend of liquid sweeteners, flavor concentrates, acidulants, and coloring agents. High fructose corn syrup or liquid sugar arrives in tanker trucks and is pumped directly into insulated storage silos. From there, metering pumps draw exact amounts of sweetener into stainless steel mixing vessels. Each vessel is jacketed for temperature control and fitted with high-speed impellers. Flavor compounds are stored in temperature-regulated vats and dispensed in minute quantities using servo-controlled dosing systems. Each component is added in a fixed sequence to ensure homogenization and prevent chemical interaction before full dilution. Citric and phosphoric acid are added next via automated dosing units, lowering the pH and adjusting taste profile. Caramel color is injected through pressurized nozzles in measured bursts, darkening the mixture. After all ingredients are blended, the syrup passes through a plate heat exchanger for flash pasteurization. Heated to above 85 degrees Celsius for under 30 seconds, the syrup is then rapidly cooled to preserve flavor integrity. The syrup is piped into chilled storage tanks, each lined with food-grade epoxy to prevent contamination. These tanks are agitated at controlled RPMs to keep the syrup uniform. From this point, the syrup is mixed with the purified water. This occurs inside a continuous blending unit known as a proportioner. The unit draws both syrup and water in a 1:5 ratio using synchronized flow meters and magnetically actuated valves. Flow rates are adjusted dynamically based on inline refractometers that monitor sugar concentration in real time. Any deviation from target Brix level results in automatic recalibration of fluid inputs. The mixture then enters a deaeration chamber where it is subjected to vacuum pressure to remove entrained oxygen and carbon dioxide, which can affect taste and carbonation efficiency. Following deaeration, the liquid enters a carbonator. Inside a sealed stainless steel vessel, the beverage is chilled to near freezing temperatures to increase gas solubility. Liquid carbon dioxide is injected into the drink through a diffuser plate with thousands of microperforations. The gas dissolves rapidly under high pressure, saturating the beverage with carbonation. Rotary carbon pumps recirculate the liquid within the chamber to ensure uniform CO2 distribution. Carbonation levels are continuously monitored by inline gas volume analyzers. The carbonated beverage is held in pressurized buffer tanks, awaiting transfer to the filling line. The filling process begins with bottle or can preparation. Empty containers arrive via conveyor belts in nested stacks or crates. A depalletizer equipped with vacuum grippers lifts layers of containers and places them onto the in-feed conveyor. Containers proceed through a rinser unit that inverts each one and blasts filtered air or sterile water inside to dislodge debris. The containers are then uprighted and transferred to the filler carousel. The filling machine features multiple heads, typically between 40 to 120, arranged in a rotary configuration. Each head is fed from the pressurized carbonated beverage tank. As a container aligns with a filling head, it is clamped and sealed. Counter pressure is applied to prevent foaming. A filling valve opens and the product is gravity fed or gently pumped in. As the container fills, vent tubes displace internal gas to maintain pressure equilibrium. Once full, the valve closes and the container is released. Immediately after filling, containers proceed to the capping station. In bottle lines, caps are sorted and oriented using centrifugal feeders. Each cap is dropped into position and pressed onto the bottle using pneumatic or servo-controlled spindles. Torque sensors ensure proper seal strength. For cans, lids are fed through chutes and placed atop the can mouth. A seaming head engages, folding and curling the lid's edge around the can's rim to create a hermetic seal. The container is then released to a discharge conveyor. Sealed containers pass through an inline quality control system. High-speed vision sensors inspect each container for correct fill height, cap application, label alignment, and structural integrity. Any defective item is ejected via air-jet nozzles. Simultaneously, select containers are diverted for destructive testing. These include pressure retention tests, carbonation level checks using digital pierce testers, and torque measurements for closure tightness. Approved containers proceed to labeling. Bottles pass through a label applicator fitted with servo-driven rollers. Pre-printed labels on adhesive rolls are cut and transferred using vacuum drums. Each label is wrapped and smoothed onto the bottle's surface using motorized brushes. Can lines use shrink sleeve applicators? Sleeves are dropped over the cans and pass through a heat tunnel where forced air heaters contract the film around the container body with uniform tension. Each labeled item is scanned by barcode readers to verify correct SKU association. Labeled products travel to the packaging area. Containers are grouped into multi-packs using high-speed collators. For bottles, robotic arms or pneumatic sweepers push groups of 6, 12, or 24 into cardboard carriers or plastic overwrap. For cans, shrink film machines envelop the groupings with polyethylene film. The packs pass through shrink tunnels where the film tightens around the cans. Heat is applied via convection blowers at calibrated temperatures to avoid deformation. Finished multi-packs are conveyed toward case packing stations. Corrugated cartons are erected from flat blanks by automated formers and transported via belt to loading stations. Pneumatic. Pushers slide each multi-pack into its case. In robotic systems, Delta robots or articulated arms equipped with suction grippers lift and place products with extreme precision, adjusting in real time for orientation variances detected by machine vision. Loaded cartons proceed to automatic tapers that seal the top flaps with pressure-sensitive adhesive tape or hot melt glue. Sealed cases continue to the palletizing area. Pallet dispensers drop wooden or plastic pallets onto powered rollers. A layer building system positions cases in pre-programmed patterns for structural stability. Robotic arms or gantry-style palletizers pick cases and place them in rows, adjusting height via vertical actuators. Each layer may be interleaved with a slip sheet for added stability. Once a pallet is complete, a wrapping station envelops it in stretch film. The turntable spins while a vertical arm applies film under tension, binding the load tightly. The process for Sprite begins with the transformation of municipal water into beverage-grade base water. This water enters through insulated pipelines and is immediately routed into a sequence of stainless steel treatment vessels. First, it flows through a coarse mechanical screen to eliminate large particles. It then enters a pressurized sand filtration unit filled with graded quartz media, where finer solids are trapped. After this, the water moves into an activated carbon filtration chamber. Here, as it passes through beds of carbon granules, residual chlorine, organic molecules, and off odors are removed through adsorption. Next, the water is softened in a dual-tank ion exchange system. Calcium and magnesium ions are replaced with sodium ions to prevent mineral buildup in downstream equipment. From there, it proceeds into a reverse osmosis module, which uses pressure-driven membrane filtration to remove dissolved salts, nitrates, and bacteria. The output is ultra-clean water with consistent properties. Before storage, it is exposed to ultraviolet irradiation and passed through a 0.2 micron sterile filter to eliminate any remaining microbes. The treated water is directed into large, sealed stainless steel tanks fitted with slow-turning paddles that keep the fluid agitated and uniform in composition. Meanwhile, the flavor syrup is prepared in a separate, climate-controlled mixing room. The process begins by transferring liquid sweeteners, either high fructose corn syrup or refined liquid sucrose, from bulk storage tanks into jacketed blending vessels. These vessels are equipped with load cells to ensure exact quantities are used. Agitators start spinning to ensure even distribution. Into these vessels, concentrated flavor ingredients are injected using computer-controlled microdosing pumps. These include lemon lime oil emulsions, natural citrus flavor distillates, and bitterness balancers. Citric acid is added as the key acidulant to provide Sprite's distinct tart profile. Sodium citrate is introduced to regulate the beverage's buffering capacity and stabilize acidity. Small quantities of preservatives are introduced last. The mixture is kept under continuous motion with variable speed impellers that prevent stratification. Once all components are incorporated, the syrup is heated rapidly in a tubular heat exchanger, held at pasteurization temperature for a brief duration, and then chilled through a countercurrent cooling system. Once cooled, the syrup is passed through a sterile filter and stored in closed-loop storage tanks under positive nitrogen pressure to prevent contamination. The next phase is inline blending. In this stage, the finished syrup is metered into a continuous stream of purified water. The blending takes place inside a high-precision mixing manifold, where magnetic flow meters monitor the real-time ratio of syrup to water. Proportional integral derivative controllers adjust valve positions automatically to maintain a consistent blend ratio. Inline refractometers provide Brix readings that validate sugar concentration. Once the beverage stream is formed, it moves into a deaeration tank where vacuum pumps lower the internal pressure to remove dissolved oxygen. This step is critical to improve carbonation absorption and prolong product stability. The deaerated mixture then flows into a cooling module that chills the liquid to near 0 graus Celsius using a glycol-based refrigeration loop. Lowering the temperature increases the solubility of carbon dioxide in the next step. Carbonation takes place in a pressurized tank equipped with high-efficiency diffusers. Liquid CO2 is injected under controlled pressure through stainless steel sparges that break the gas into fine microbubbles. As these bubbles rise through the cold beverage, the carbon dioxide dissolves into the liquid under saturation pressure. A circulation pump ensures the beverage continuously cycles through the carbonation chamber for uniform gas distribution. Inline gas volume analyzers measure the carbonation level in real time, while PID loops adjust CO2 flow rate and internal pressure accordingly. The carbonated product exits into a buffer tank held under constant pressure, ready for filling. Container preparation is a continuous process occurring in parallel. PET bottles or aluminum cans arrive from high-speed depalletizers that remove layers of empty containers using suction pads and robotic arms. The containers are placed onto conveyor belts and directed toward the rinsing system. For bottles, an inverted air rinse machine uses ionized air jets to dislodge any debris inside. Cans are washed with sterile water sprays and dried with compressed air. Once cleaned, the containers proceed toward the rotary filler. Filling occurs on a multi-head rotary machine where containers are positioned under filling valves arranged in a circular turret. The carbonated beverage is delivered from the pressurized buffer tank to the filler bowl. Each container is raised into position and sealed against a filling nozzle. First, the internal pressure of the container is equalized using a pre-evacuation chamber. Then, the valve opens and liquid flows in under gravity or slight overpressure. Vent tubes allow displaced gas to escape without disrupting carbonation. Once the container reaches its calibrated fill height, the valve closes and the container is lowered back onto the conveyor. Capping follows immediately. For bottles, caps are sorted and oriented using centrifugal feeders and fed into a rotary capper. Each cap is pressed onto the bottle and secured using torque-regulated chucks. Sensors verify cap presence and alignment. For cans, ends are placed on top by an end-feeding chute, and a seaming head curls the lid over the rim in a multi-stage process to form a hermetic seal. Once sealed, the containers pass through a pressurized water spray or vacuum chamber to remove any residual product from the exterior. The sealed containers move toward quality assurance. Systems. High-speed cameras check for correct fill levels, proper capping, and label placement. Infrared sensors detect internal pressure by analyzing surface deformation. Some containers are automatically diverted for destructive testing, including carbonation loss, torque verification, and microbiological sampling. Labeling varies by container type. For PET bottles, self-adhesive labels are applied using servo-driven applicators that wrap labels around the cylindrical surface. The applicator head synchronizes with container speed and uses rubberized rollers to press the label into place. In canning lines, shrink sleeves are applied over the containers, and the cans pass through a steam or infrared tunnel that contracts the film tightly around the can body. Optical sensors verify label presence, orientation, and print clarity. Labeled containers are grouped into multi-unit packages by a high-speed collation system. Bottles are mechanically pushed into plastic carriers or enclosed in cardboard sleeves using servo arms. Cans are collected into 6-packs or 12-packs and overwrapped in shrink film. The multi-packs then pass through a shrink tunnel where hot air circulates uniformly around the film, causing it to contract tightly without damaging the product inside. Packaged units are routed to case packing stations. Here, automatic erectors construct corrugated cases from flat blanks using glue or tape. Robotic loaders with vacuum end effectors pick up groups of bottles or cans and place them into the open cases in pre-programmed formations. The filled cases are sealed at the top using either hot melt adhesive applicators or pressure-sensitive tape dispensers. Cases proceed to palletization. Empty pallets are dispensed from a stack onto a conveyor. A layer-forming system organizes cases into a stable pattern using motorized guides and pusher arms. A robotic palletizer or gantry system transfers each layer onto the pallet, adjusting height and position after each pass. Between layers, slip sheets may be inserted to enhance stacking integrity. Once fully stacked, the pallet is moved into a stretch wrapping station. A rotating turntable spins the pallet while a film carriage moves vertically, wrapping the entire stack in tensioned polyethylene film to secure the load. The Canada Dry production process begins with the intake and treatment of raw water. Municipal water is directed into a series of pre-treatment systems through stainless steel pipelines. The first step is mechanical filtration, where water flows through mesh strainers that remove coarse particulates. Following this, it passes through a dual media sand and anthracite filtration system to eliminate finer suspended solids. The next stage is activated carbon filtration. As the water moves slowly through the carbon beds, chlorine, chloramine, and organic contaminants are removed through adsorption. The water is then softened using a sodium-based ion exchange system that exchanges calcium and magnesium ions for sodium ions, reducing scale formation in downstream equipment. After softening, the water is subjected to reverse osmosis using high-pressure pumps to force it through semi-permeable membranes that separate out dissolved solids, bacteria, and unwanted ions. The treated water then undergoes ultraviolet sterilization and sub-micron filtration to achieve microbiological purity before being transferred to agitated, sealed stainless steel storage tanks for use in the product blend. Parallel to this, the syrup production begins in a closed system syrup room. Liquid sweeteners, such as high fructose corn syrup, are delivered in heated tankers and pumped into bulk storage silos lined with food-grade coatings. These silos are equipped with volumetric flow meters and thermal controls. The sweetener is metered into stainless steel mixing vessels using precision dosing pumps. These vessels are jacketed for thermal regulation and include bottom-mounted mixers driven by variable frequency motors to achieve high shear mixing. Ginger extract, lime oil, lemon oil, and proprietary spice emulsions are stored in temperature-controlled dosing cabinets and delivered via sealed piping to the blending tanks. Dosage is governed by recipe management software, with peristaltic pumps calibrated for microdosing accuracy. Citric acid is introduced to provide tartness, followed by potassium sorbate or sodium benzoate as preservatives. Caramel color, if used, is injected through positive displacement pumps, controlled to a fraction of a milliliter per liter. Once all components are in the tank, the syrup undergoes a high shear mixing cycle. After homogenization, it is flash pasteurized by pumping through a plate heat exchanger system, reaching temperatures above 85 Celsius for a few seconds, and then rapidly cooled using a countercurrent chilling loop. The syrup is passed through sterile filters and transferred into insulated holding tanks with nitrogen blankets to prevent oxidation and maintain flavor integrity. With syrup and water prepared, they are combined using an inline blending system. This unit uses magnetically driven flow meters to monitor real-time volumetric flow of each stream. PID-controlled valves adjust the ratio continuously to maintain the programmed syrup-to-water proportion. The blend passes through a series of mixing chambers where turbulence is created using static mixers to ensure full molecular integration. An inline refractometer measures the resulting Brix level, and adjustments are made automatically to ensure target sweetness is met within plus 0.1 Brix. After blending, the mixture is deaerated in a vacuum vessel. Liquid enters a chamber under reduced pressure, causing entrained oxygen and other gases to escape. The deaerated product is immediately cooled through a glycol-based plate chiller to a temperature just above 0 degrees Celsius, maximizing carbon dioxide solubility in the next step. The cold, deaerated blend is sent to the carbonation module. Here, liquid CO2 is introduced into the beverage via high-precision sparging rings located at the base of the carbonation tank. The tank operates under constant high pressure and uses recirculation pumps to keep the liquid moving over the gas interface, improving dissolution rates. Carbonation levels are controlled through feedback loops tied to gas volume analyzers that measure dissolved CO2 in real time. Once carbonated, the product is routed through pressurized transfer lines to filling buffer tanks. These tanks maintain positive pressure to prevent gas loss and are fitted with level sensors and pressure regulators. Container preparation runs in parallel. Empty aluminum cans or PET bottles are delivered via automated depalletizers that use vacuum pads or mechanical sweep arms to remove layers of containers and place them on conveyor systems. The containers pass through a cleaning unit where they are inverted and rinsed internally with filtered, ionized air or sterile water. Any residual moisture is blown off using high-velocity air knives. Clean containers proceed to the filling carousel. The filling system consists of a rotary filling machine with 60 to 120 heads, depending on capacity. Each container is raised into position against a filling valve. The system first applies counter pressure to match internal carbonation levels and prevent foaming. Filling valves open when pressure equalization is achieved. Product flows into the container through gravity or gentle pressurization. During fill, displaced gas vents through a return tube to maintain equilibrium. Fill volume is controlled by valve timing or volumetric flow measurement. Once filled, the valve closes and the container is lowered back to the conveyor. Capping occurs immediately after filling. For bottles, closures are delivered by an oriented cap feeder using centrifugal force. Caps are guided into a chute and pressed onto bottles by servo-controlled capping heads with adjustable torque settings. For cans, aluminum ends are fed into place from a lid magazine. A seamer head performs a double-fold operation, curling the lid's flange over the rim of the can and compressing the metal layers together to form an airtight seal. Sensors verify each seal, and containers with improper application are ejected from the line. Filled and sealed containers are conveyed through a vision inspection system equipped with high-speed cameras and LED backlighting. Algorithms analyze fill height, cap placement, and label orientation. Infrared sensors check for proper internal pressure via deformation profiles. Containers that do not meet specification are removed from the line using pneumatic pushers. Labeling systems vary by format. PET bottles pass through wraparound labelers that apply pressure-sensitive or roll-fed film labels. Servo motors control label placement, while rubber rollers press labels onto the surface. Cans use shrink sleeve applicators, where sleeves are dropped over the container body and pass through a heat tunnel. The tunnel uses either infrared or steam heat to contract the film evenly around the can. Label inspection units verify barcode readability, positioning, and design accuracy. The finished containers are then grouped into multi-packs. Bottles are sorted and arranged into clusters using pneumatic sweep arms and placed into molded plastic carriers or corrugated trays. Cans are conveyed into shrink wrapping units, where sets of 6, 12, or 24 are collated onto a moving belt. Polyethylene shrink film is dispensed over the groups and sealed at the edges. The packages move through a heated tunnel with recirculated hot air that shrinks the film tightly around the cans, securing them in a stable bundle. Multi-packs advance to the case packing area. Automatic case erectors unfold corrugated blanks into boxes and place them on a conveyor. Robotic gantries fitted with suction grippers pick up multiple multi-packs at once and lower them into open cases. Depending on format, cases may be closed using tape applicators or hot melt glue systems. Completed cases are scanned for contents, weight, and closure integrity using inline check weighers and vision systems. Palletizing begins with pallet dispensing. Wooden or plastic pallets are fed from a vertical stack onto a chain conveyor. Robotic palletizers equipped with multi-axis arms arrange cases on the pallet in interlocking patterns to maximize stability. Slip sheets may be inserted between layers using vacuum pick-and-place units. Once stacking is complete, the pallet moves into an automatic stretch wrapper. Here, the pallet is spun on a turntable while a film carriage applies tensioned polyethylene film around the load. The film is heat sealed at the end of the cycle. and the wrapped pallet is discharged to a staging conveyor. Industrial ice cream production begins with the preparation of the liquid mix base. Raw ingredients used in the base include milk or milk solids, cream or anhydrous milk fat, sweeteners such as sucrose or glucose syrup, stabilizers, emulsifiers, and optional flavoring agents. Bulk liquid dairy components are stored in temperature-controlled stainless steel tanks connected to automated dosing lines. Milk fat content is measured using inline infrared sensors to meet formulation targets, typically between 8 and 12% depending on the product specification. Sweeteners such as granulated sugar or glucose syrup are stored in dry bins or heated tanks. Sugar is conveyed using auger screw feeders into blending tanks, while glucose syrup is pumped through jacketed pipelines at a regulated temperature between 45 and 60 degrees Celsius to maintain viscosity. Stabilizers and emulsifiers such as guar gum, mono and diglycerides, or carrageenan are added in precise quantities using dry ingredient feeders with load cell controlled hoppers. All components are blended in high capacity, jacketed stainless steel mix tanks equipped with high shear agitation. Mixing durations and shear rates are pre-programmed and adjusted based on batch size and viscosity targets. The mixture is heated uniformly to 70-85 degrees Celsius using indirect steam in the jacket to fully dissolve solids and activate emulsification agents. This thermal processing step homogenizes the mixture and ensures complete dispersion of the fat phase. The hot mix is then passed through a homogenizer at pressures ranging from 1500 to 2500 psi. This high-pressure two-stage process reduces the size of fat globules, creating a stable emulsion and improving mouthfeel and overrun stability. Homogenization is measured and recorded by inline pressure transducers and flow meters. Once homogenized, the mix is immediately cooled to below 5 degrees Celsius using plate heat exchangers. The cooled mix is transferred to aging tanks and held between 2 and 5 degrees Celsius for a period of 4 to 24 hours, depending on product type. During aging, the fat crystallizes and proteins hydrate, which enhances body, texture, and whipping properties. Aging tanks are equipped with low-speed agitators to maintain uniformity without incorporating air. After aging, the mix is pumped into continuous freezers. These machines are equipped with scraper blades and barrel chillers. The mix enters at 2 to 5 degrees Celsius and is rapidly frozen as it moves through. The freezing cylinder cooled to approximately 20 to 25 degrees Celsius using ammonia or freon-based refrigeration systems. The freezing barrel incorporates air into the mix during agitation. The amount of air added is called overrun, typically maintained between 60 and 100% by volume using controlled air injection valves synchronized with pump speed. The partially frozen ice cream exiting the continuous freezer has a temperature of 5 to 7 degrees Celsius and a semi-solid texture. From this point, the product flow diverges based on packaging format. For bulk containers, the ice cream is extruded directly into tubs or pails using piston or rotary fillers. For single-serve novelties or molded formats, the product enters downstream portioning or molding stations. In extrusion-based forming systems, the semi-solid ice cream is extruded through stainless steel nozzles onto a moving stainless steel belt, cooled to 40 degrees, using cryogenic cooling elements. The belt carries the formed shapes under a quick freeze chamber, where additional cold air is blown to firm up the shape. Inline sensors monitor form consistency and weight. Shapes are cut by ultrasonic or wire blades synchronized with belt movement. In molded systems, the ice cream is deposited into polycarbonate molds that travel on a carousel immersed in a brine solution held at 25 to 30 degrees. Product solidifies inside the mold within 8 to 12 minutes, depending on volume. Once hardened, sticks are inserted mechanically into the semi-solid mass using servo-driven arms. Demolding is achieved by briefly dipping molds into warm water baths and using pneumatic pistons to eject the bars. Fillings, inclusions, and variegates are added at multiple points. For layered products, rotary depositors add jams, caramel, or chocolate syrup between ice cream layers. Inclusion feeders dose chocolate chips, cookie pieces, or nut fragments into the flowing stream before extrusion using volumetric or gravimetric feeders. Variegates are added, using swirl nozzles or rotating spouts that inject sauces in spiral patterns into tubs. Enrobing stations apply chocolate coatings to frozen bars using curtain coaters or immersion tanks. Bars are transported on wire belts and pass through a curtain of liquid chocolate held at 30 to 35 degrees each. Excess coating is blown off using air knives. Coated bars pass through a set zone where the chocolate is tempered and solidified using directed cold air streams. Toppings such as nut granules or cookie crumbs are applied to the wet coating via vibratory sprinklers before hardening. Once the shape is stabilized and the product fully frozen, packaging begins. Products are loaded into flow wrapping machines or form-fill seal machines. Printed film is drawn from reels, formed around the product, and sealed using heated jaws and pressure. Modified atmosphere flushing may be applied to reduce oxygen exposure. Each package is marked with batch codes and expiry dates via inkjet or laser printers. Packaged products proceed to check weighers and metal detectors for final inspection. Weighing systems use dynamic load cells to ensure each item is within +get 1% of target weight. Metal detectors with triple coil arrays scan for ferrous, non-ferrous, and stainless steel contamination. Rejected products are removed automatically from the line and logged in the manufacturing execution system. After inspection, individual packages are sorted into multi-packs or cartons using robotic collators and carton erectors. Units are loaded into retail-ready boxes, sealed with glue or tape and labeled with barcode identifiers. Cartons are stacked by robotic palletizers into programmed patterns based on load configuration and distribution route. Stretch wrapping machines secure pallets with film before warehouse transfer. In frozen storage, pallets are maintained at 25 degrees RC or colder. Pallet locations are mapped using barcode scanners integrated into warehouse management software. Products remain in frozen inventory for no more than the shelf life period assigned to each SKU. Rotation is enforced using first expiry, first out logic based on lot and production timestamp. The entire process is supported by centralized SCADA systems that monitor temperature, viscosity, pressure, weight, flow rate, air injection volume, and cooling intensity at every stage. Each unit of ice cream is fully traceable to its ingredient lots and production conditions through digitized batch records stored in the ERP system. The production of frozen yogurt in a factory begins with the preparation of the liquid mix base, which consists of dairy solids, sweeteners, live yogurt cultures, stabilizers, emulsifiers, and water. Each component is handled in isolated supply systems to ensure batch-to-batch consistency before integration. The mix formulation is calculated to achieve a target fat content of 2 to 4%, milk solids non-fat of 8 to 12%, and a final total solids content between 30 and 38%, depending on the product type. Bulk dairy ingredients, such as skimmed milk, whole milk, and cream, are stored in stainless steel, temperature-controlled silos or tanks held between 1 and 4 Allency. These tanks are fitted with slow-speed agitators to prevent fat separation and sedimentation. From the tanks, ingredients are drawn through dedicated pipelines with volumetric flow meters that measure and regulate dosing rates with tolerances within +0.2%. Sweeteners such as sucrose, glucose syrup, fructose, or high fructose corn syrup are stored in either crystalline form or heated tanks depending on their physical state. Crystalline sugars are conveyed to mixing tanks via screw feeders or pneumatic conveyors, while liquid syrups are pumped through heated, jacketed pipes to maintain constant viscosity. The addition rates of each sweetener are determined by pre-programmed recipes in the batching software and are adjusted in real time based on inline refractometers measuring total soluble solids. Stabilizers and emulsifiers such as guar gum, carrageenan, mono and diglycerides, or cellulose derivatives are pre-blended into dry mixes and introduced using vacuum powder hoppers into blending tanks containing preheated water at 60 or 70 degrees Celsius. This temperature is critical for full hydration and dissolution. Agitation is applied using high shear impeller mixers, ensuring uniform dispersion and hydration within 15 to 20 minutes. Viscosity is monitored continuously via inline rotational viscometers, and any deviation triggers automatic adjustment to the water feed rate or agitation speed. Once all ingredients are combined, the resulting mix is pasteurized using a continuous high-temperature, short-time HTST pasteurizer. The pasteurization process typically operates at 85 Celsius for 30 seconds to ensure microbial reduction without altering flavor or functional properties. The system includes balance tanks, timing pumps, regeneration sections, holding tubes, and cooling exchangers. Temperature probes and flow controllers verify that critical control parameters are met for every liter of mix. Any batch failing to meet time temperature integration is automatically diverted to a reject tank. Following pasteurization, the mix is homogenized in a two-stage homogenizer at pressures between 1500 and 2500 psi. The first stage breaks down fat globules to sub-micron sizes, promoting a stable emulsion, while the second stage disperses protein aggregates evenly throughout the mix. Homogenization ensures a smooth mouthfeel, prevents cream separation, and enhances the stability of the yogurt base during frozen storage. The homogenized mix is rapidly cooled to 4 degrees Celsius using a plate heat exchanger and transferred into agitated aging tanks. These stainless steel tanks have capacities ranging from 2,000 to 20,000 liters and are equipped with low-speed paddles to maintain uniform suspension without introducing air. The mix is aged for 4 to 24 hours depending on the formulation. During this aging period, fat crystallization and protein hydration take place, improving the whipping properties and final texture of the frozen yogurt. After aging, the next stage is inoculation with live yogurt cultures, a pre-prepared, freeze-dried culture blend containing specific strains of Lactobacillus, Bulgaricus, and Streptococcus thermophilus is rehydrated and activated in a sterile environment, then introduced into the aged mix in precise ratios. The inoculated mix is transferred to fermentation tanks equipped with temperature control systems. The mixture is held at 43 degrees Celsius for 4 to 6 hours, during which lactic acid is produced, reducing pH from above 6.5 to around 4.5. The acidification process causes protein coagulation, giving the base its distinctive yogurt flavor and slightly thickened texture. Once fermentation reaches the target pH, it is immediately halted by cooling the mix to below 8 degrees Celsius. This temperature shock preserves the live cultures and stabilizes the flavor. From here, the yogurt base may be held in intermediate storage for up to 24 hours before being processed further. If flavorings or colorants are required, they are added post-fermentation to preserve the viability of the live cultures. These additives are introduced through inline dosing pumps, controlled by magnetic flow meters for precise delivery. The chilled fermented yogurt mix is transferred to the continuous freezing units. These industrial freezers use scraped surface barrel designs, where the yogurt base is frozen while being continuously agitated by rotating blades. The barrel wall is chilled to between 20 and 30 degrees Celsius using ammonia or freon-based refrigeration systems. The rotating blades prevent ice crystal growth by constantly scraping the frozen layer from the barrel wall and remixing it into the semi-frozen matrix. During freezing, air is incorporated into the mix to achieve a desired overrun of 30% to 60% by volume, much lower than regular ice. Cream to maintain the dense, creamy consistency associated with frozen yogurt. The air injection rate is precisely controlled using mass flow controllers and synchronized with product flow rate. The resulting product exits the freezer at a temperature of 5 to 7 degrees Celsius and has a soft serve consistency. If inclusions such as fruit pieces, chocolate chips, or granola clusters are required, they are introduced at this stage using rotary feeders or auger-based inclusion systems. These systems are calibrated to dispense particulate matter based on mass or volume per unit of frozen yogurt. Inclusions are mixed gently into the flow using low shear blending heads to avoid damaging texture or shape. Forming and portioning depend on the packaging format. For cups and tubs, rotary or piston fillers dispense the frozen yogurt into containers on an indexed conveyor line. Fill levels are verified using laser height sensors or load cells beneath the filling stations. The containers are then lidded using pick-and-place robots, followed by heat sealing or snap lid application depending on the package design. For stick products or novelty bars, the yogurt is extruded into polycarbonate molds mounted on a carousel or linear track. The molds pass through a 30°C brine bath or air blast freezer for rapid hardening. Once the product reaches a core temperature of 18 degrees, sticks are inserted using servo-controlled plungers. The molded products are then released from the molds using brief exposure to warm water spray or ultrasonic demolding mechanisms. Products requiring enrobing are transferred to chocolate coating stations. Bars move on a mesh belt through a curtain of tempered chocolate or compound coating held at 32 to 34 degrees Celsius. Excess coating is removed using air knives, and toppings such as crushed nuts or cookie bits are sprinkled over the wet coating before it hardens in a subsequent cooling tunnel maintained at 15 degrees Celsius. Every unit, whether in cup, tub, or stick format, is passed through flow wrappers or form-fill seal machines. Packaging film is drawn over a forming collar, heat sealed along longitudinal and transverse axes, and printed with lot numbers and expiration dates using thermal inkjet systems. Products are checked on inline check weighers for mass accuracy, then metal detected using balanced coil systems capable of detecting contaminants down to 1.0 mmHg ferrous equivalents. Packaged frozen yogurt units are grouped into multi-packs or retail cartons using robotic pick-and-place systems. Cartons are sealed with hot melt glue and printed with barcodes and logistics identifiers. Palletizing robots stack cartons in programmed configurations. Each pallet is wrapped using rotary stretch wrapping machines and moved into blast freezers or deep storage warehouses. Frozen storage areas maintain air temperatures between 25 and 30 degrees Celsius, with controlled airflow to preserve texture and prevent ice recrystallization. Each pallet is tagged with barcodes that link to a warehouse management system, allowing full traceability of production date, ingredient lots, shift information, and packaging batch. The factory production of sorbet begins with the precise formulation of a base mix that typically consists of filtered water, fruit puree or juice concentrates, a combination of sugars, stabilizers, and acidulants. These ingredients are sourced in bulk and stored in isolated silos, refrigerated tanks, or powder silos based on their form and storage requirements. Before batching begins, each raw material is passed through automated intake stations where flow rate, weight, or volume is measured using mass flow meters or load cells to ensure formulation precision to the second decimal. The main batch tank is a large stainless steel jacketed vessel fitted with dual mode agitation, one high shear impeller and one slow-speed anchor scraper to manage the simultaneous dispersion of powders and gentle circulation of the mix. The process begins by pumping deionized water into the tank. This water is processed through reverse osmosis filters to reduce mineral content and stabilize the flavor profile. Temperature of incoming water is held at 60 to 70 degrees Celsius to accelerate sugar dissolution and aid in the hydration of stabilizers later in the cycle. Fruit inputs, often high viscosity purees or concentrates, are pumped from cold storage tanks maintained at 4 rengangs. These tanks are fitted with bottom-mounted paddle stirrers to prevent sedimentation of pulp or particulate matter. The fruit component is introduced via jacketed stainless lines with rotary lobe pumps that preserve particulate integrity and ensure steady laminar flow. Inline flow meters measure delivery in real time, adjusting valves based on programmable batch set points. Sweeteners are introduced in multiple phases depending on their type. Crystalline sugars, such as sucrose or dextrose, are stored in bulk bag unloaders and conveyed to the tank using vacuum-driven feeders or screw. Augers passing through sieve screens to remove agglomerates. Liquid sweeteners like glucose syrup or high fructose corn syrup are pumped from preheated tanks through jacketed lines at temperatures between 40 and 60 degrees Celsius to reduce viscosity. All sugar additions are monitored using an inline refractometer, which continuously reads the brix level and automatically adjusts feed rates to ensure consistency in total soluble solids. Stabilizers and emulsifiers, including locust bean gum, guar gum, or pectin blends, are pre-dispersed into a slurry using a high-shear induction system connected to a secondary mixing tank. The system uses a Venturi-driven powder funnel that draws dry powders into a vortex of hot water, while shear blades break down clumps. The hydrated stabilizer solution is then metered into the primary batch tank over several minutes to allow for uniform dispersion. Viscosity is tracked by an inline rotational viscometer, while flow rate is synchronized with the agitator speed to prevent localized gelation. Acidulants are introduced once the temperature drops below 60 degrees Celsius to preserve their functional integrity. Citric acid and malic acid are most commonly used, added via microdosing pumps based on real-time pH feedback from inline probes. The typical pH target range for sorbet mix is between 3.4 and 4.2, depending on fruit type and desired tartness. Some blends may also include buffering salts or fruit-derived aromatic extracts, introduced in sub-gram quantities with gear-driven precision pumps. Once the mix is fully blended, the entire volume is passed through a plate or tubular heat exchanger for pasteurization. The product is heated to between 82 and 90 degrees Celsius for a holding period of 20 to 30 seconds using a hot water loop on the heating side of the exchanger. Flow rates are calibrated to ensure that each liter achieves the required thermal profile. Temperature probes at the inlet, outlet, and holding tube ensure compliance with the time temperature curve. Any deviation from set points automatically diverts the mix to a rework tank using pneumatically controlled valves. Following pasteurization, the mix is rapidly cooled to 4 degrees Celsius using chilled glycol in the final section of the exchanger. It is then pumped to aging tanks, insulated, vertical stainless steel silos with gentle agitators. The mix is held for 4 to 24 hours, depending on stabilizer type, allowing the hydration of hydrocolloids and maturation of flavor. During aging, key metrics including brix, viscosity, pH, and color are measured at regular intervals using inline and lab-based sampling. After aging, the mix is transferred to continuous freezers for dynamic freezing. These are horizontal barrel type scraped surface heat exchangers with internal rotors spinning at high speed. The internal barrel is cooled by ammonia or freon-based refrigerant, keeping the wall temperature at 25 degrees Celsius to 30 degrees Celsius. The mix is pumped into the barrel at 4 degrees Celsius and partially frozen in under 30 seconds. Rotor blades scrape frozen mix from the walls, maintaining even temperature distribution and preventing ice crystal buildup. At this stage, air is injected into the freezing chamber to achieve controlled overrun. For sorbet, overrun levels are typically between 10 and 30%, maintained using mass flow controlled air injection, synchronized with product throughput. Air pressure, temperature, and flow rate are logged continuously. The exit temperature of the product from the freezer is typically 5 degrees Celsius to 7 degrees Celsius, with a soft serve consistency suitable for depositing. At the point of extrusion, some product formats receive inclusions or variegates. For inclusion, dry or semi-moist elements like fruit pieces, citrus peel, or coconut shreds are fed through a belt-based dosing unit with weigh cell feedback. The feeder aligns with the product stream and deposits inclusions just before it enters the filler. Variegates, such as raspberry swirls or mango sauce, are injected via multi-nozzle swirl heads using positive displacement pumps, synchronized with container indexing to create layered or spiral visual effects. The filling system uses rotary or linear piston fillers with programmable dose volumes. Fill heads descend into the container, release the product in a bottom-up motion to prevent air entrapment, and retract at the end of the fill cycle. Laser height sensors verify the final fill level to ensure consistency. For products with decorative topping, a secondary depositor adds surface sources, fragments, or textured swirls before lidding. Filled containers are sealed with pre-cut lids or heat-sealed films. Lidding stations use servo-driven arms and apply uniform pressure to ensure adherence. Date coding and batch marking are applied using thermal inkjet or CO2 laser systems immediately after sealing. Each pack is passed through a metal detector, which uses multi-frequency coils to detect foreign metallic objects within the sealed product. Immediately post-packaging, the product enters the hardening tunnel. This is a spiral or straight belt blast freezer, where ambient air temperature is held at 35 to 45 degrees Celsius. Air is circulated at high speed to ensure fast freezing rates. Dwell time inside the tunnel ranges from 30 to 90 minutes, and the goal is to reduce the core temperature of each unit to below just 18 degrees Celsius. Faster hardening reduces ice crystal size and improves long-term texture stability. Core temperatures are verified by infrared sensors or penetrating thermocouples on randomly sampled units. Hardened products are conveyed to automated carton packers. A vision system identifies each container's orientation and positioning. Robotic arms equipped with suction grippers or mechanical clamps group units into clusters and load them into pre-erected cartons. Cartons are sealed using hot melt adhesive or tape, then labeled using a print and apply labeling system. The label includes SKU identifiers, lot number, date, and logistics barcodes. Cartons are then routed to the palletizer. Layers of cartons are stacked according to a programmed pattern to optimize pallet stability and maximize transport efficiency. Stretch wrapping machines encase each pallet in multi-layered film with preset tension profiles to secure the load during transport. Pallets are labeled with SSCC codes and sent to deep freeze storage, where ambient temperature is maintained between 25 and 30 degrees C. Storage location is recorded in a warehouse management system using RFID or barcode scanning. Each batch of sorbet is traceable through electronic production records, linking ingredient lots, formulation parameters, processing times, and packaging data. Digital records include metrics for pasteurization, Brix values, overrun, pH, freezing rate, fill weight, inclusion density, and packaging inspection results. Production lines are modular and allow for multiple flavor variants and packaging formats. Line changeovers are performed by CIP, clean-in-place cycles, product purges, and recipe uploads via the SCADA interface. Automated valves and sensor diagnostics reduce downtime between batches. Lines may produce up to 8,000 litres of finished sorbet per hour, depending on viscosity, inclusion complexity, and packaging speed. Ben & Jerry's ice cream is produced by combining dairy and dry ingredients in a multi-stage mixing and freezing process that integrates inclusions and variegates at high precision. The process starts with the batching of the base mix, which is composed of whole milk, cream, liquid sugars, and dry solids such as stabilizers and emulsifiers. Milk and cream are pumped from cold storage tanks into insulated blending vessels. These vessels are jacketed for thermal control and fitted with slow-speed agitators. Liquid sucrose or invert sugar is added next through metered flow lines connected to bulk sugar tanks. Dry components, including milk powder, gore gum, and mono and diglycerides, are introduced through a powder induction system located at the top of the vessel. Powder is drawn into the vortex of the liquid mix through vacuum pressure and blended evenly by the impeller. Once fully blended, the base mix is transferred through sanitary piping to the pasteurization unit. Pasteurization is carried out using a high-temperature, short-time system where the mix is rapidly heated to a fixed temperature above 80 degrees Celsius. The heated mix is held in a thermal chamber for at least 25 seconds and then cooled immediately through a regenerative heat exchanger. This brings the temperature down to 4 degrees Celsius before the mix reaches the aging tanks. Aging tanks are insulated vertical silos equipped with slow-speed agitators to maintain mix homogeneity. The mix is stored here for a minimum of 4 hours and up to 24 hours depending on formulation. During aging, fat crystallization begins and proteins fully hydrate, which improves overrun stability and mouthfeel in the final product. After aging, the cold mix is pumped to the flavoring station. At this point, base flavor ingredients such as vanilla extract, chocolate liquor, or fruit puree are injected in line using precision dosing pumps. Each flavor component is calibrated to match the target formulation and is verified through flow sensors that monitor mass per second. From here, the flavored mix enters the continuous freezer. Continuous freezers are scraped surface heat exchangers that pump the mix through a cold barrel while simultaneously injecting air. The inner barrel surface is chilled using ammonia-based refrigerant and fitted with rotating scraper blades that prevent ice buildup. As the mix travels through the barrel, it begins to freeze on the walls and is continuously scraped into a fine frozen slurry. The injected air creates overrun, which determines the density of the ice cream. Overrun is adjusted by controlling the airflow rate and pump speed and is generally kept below 50% for super premium texture. Frozen mix exits the continuous freezer at a semi-solid state and enters the ingredient feed system. This system consists of a hopper that holds dry inclusions such as cookie chunks, brownie pieces, or chocolate chips. A positive displacement auger pulls inclusions from the hopper and meters them into the ice cream flow at a controlled rate. Each piece is fed in without breaking or melting due to the low product temperature and synchronized speed control. At this stage, variegates such as caramel swirls, fudge ripples, or peanut butter ribbons are also added. These are introduced through a separate pump system that deposits the variegate in a continuous stream alongside the ice cream stream. The product then passes through a laminar blending manifold that gently folds the components together without excessive shear. The structure of swirls is preserved using channelized flow paths that direct streams into the center of the bulk flow. The fully mixed and frozen product is directed to the filling station where pre-formed containers are loaded onto an indexed carousel. Each container is aligned with a filling head that dispenses a measured volume of ice cream. Fill rate is governed by a servo-controlled piston that maintains consistent deposit weight. Once filled, the container advances to a leveling station where a rotating plate smooths the surface of the product. Some variants receive additional toppings at this stage, such as crushed nuts or fudge drizzle, which are dispensed using vibratory feeders or rotary nozzles. Filled containers proceed to lidding, where high-speed arms place and seal plastic lids onto each pint. The lids are pressed down with calibrated force to create a friction seal. The sealed pints then move to the hardening tunnel, which is a spiral freezer maintained at temperatures below -30 degrees Celsius. The product remains in this tunnel for approximately 3 hours to achieve full core hardening. Cold air is forced over the pints at high velocity to extract latent heat uniformly. Upon exiting the hardening tunnel, the pints are conveyed to the coding station where batch information is printed on the lid or bottom using inkjet printers. Following this, the pints enter the cartoning system, where mechanical pushers insert them into printed cartons for multi-pack orders. For single packs, they are collated into crates using pneumatic actuators that align units for stacking. Each crate is conveyed to a palletizing station where robotic arms stack the product according to a programmed matrix. The pallets are then shrink-wrapped and labeled before being transferred to the frozen storage warehouse. Throughout the process, temperatures are continuously monitored and recorded at all key points, including mix tanks, freezers, hoppers, filling heads, and hardening zones. Every production step is automated using programmable logic controllers connected through an industrial network. Sensors measure flow rates, temperature profiles, viscosity, deposit weights, inclusion counts, and air pressure in real time. Adjustments are made automatically to maintain consistency across thousands of units per hour. The mix composition defines final mouthfeel and thermal behavior. Pasteurization ensures phase uniformity and emulsion stability. Aging promotes protein hydration and crystal growth. Freezing governs ice crystal size and air distribution. Inclusion delivery is timed precisely to avoid damage. Variegate folding is optimized for aesthetic and structural preservation. Product texture depends on water content, fat structure, and ice distribution. Overrun level directly affects scoop resistance and volume yield. Inclusion integrity depends on size, shape, and moisture content. Ripple distribution is determined by variegate viscosity and flow channel geometry. Final hardness is a function of exit temperature and hold time in the spiral freezer. Containers are designed to withstand both vacuum during filling and pressure changes during freezing. Lid placement requires precise tolerance to avoid deformation during hardening. Pallet loads are structured to prevent toppling and to allow airflow in the warehouse. All mechanical movements are synchronized to upstream and downstream operations to prevent backup or starvation in the line. Line cleaning occurs between flavor changes using automated clean-in-place systems that flush all internal surfaces with heated detergent followed by sterile rinse. Tanks, pipes, freezers, and filling heads are cleaned without disassembly using pressurized flow circuits. Wastewater is filtered and returned to treatment before discharge. No part of the Ben & Jerry's production process is manual once ingredients are loaded into storage tanks. Ingredient handling, dosing, mixing, heating, cooling, aerating, folding, depositing, sealing, hardening, coding, packaging, and stacking are carried out in a fixed sequence controlled by machine logic. Dairy Queen Soft Serve is created through a multi-phase process that begins with the formulation of a liquid dairy mix. The mix consists of milk solids, cream, sweeteners, stabilizers, and emulsifiers, which are combined in stainless steel batching tanks. The tanks are equipped with slow-speed agitators that maintain uniform suspension of all components during hydration. Milk and cream are pumped from chilled storage tanks using sanitary centrifugal pumps. Sugar is conveyed from bulk hoppers to the mixing tank via auger-fed systems. Stabilizers and emulsifiers such as mono and diglycerides, gar gum, and carrageenan are introduced through powder induction ports. The dry ingredients are pulled into the vortex of the circulating liquid using a vacuum venturi system mounted above the mixing tank. The blended mix is agitated until all solids are hydrated and evenly distributed. Temperature in the mixing tank is gradually raised to above 65 degrees Celsius using a jacketed steam heating system. Once the desired blending temperature is reached, the mix is pumped to the pasteurization unit through insulated transfer piping. Pasteurization occurs using a plate heat exchanger which brings the liquid to 80 degrees Celsius or higher for a controlled retention time. After thermal treatment, the mix is cooled immediately to 4 degrees Celsius through countercurrent heat exchange. The chilled liquid is transferred to aging tanks, where it remains under gentle agitation for 8 to 12 hours. During aging, the fat particles begin to partially crystallize, which stabilizes emulsion and improves body and texture. Proteins and gums fully hydrate in this period, which enhances viscosity and mix performance during freezing. The aged mix is then directed to a homogenization unit. Homogenization is performed in 2 stages using a high-pressure valve assembly. In the first stage, fat globules are broken down by hydraulic shear at pressures above 1,500 pounds per square inch. The second stage ensures dispersion of remaining aggregates through pressure equalization at lower intensity. The homogenized mix achieves a uniform fat droplet size, which improves smoothness and prevents creaming. After homogenization, the base mix is cooled again to 4 degrees Celsius and held in refrigerated tanks until needed for production. When ready, the liquid is pumped to filling stations for intermediate packaging or loaded into distribution tanks if sent to retail locations. In stores, the liquid mix is fed directly into soft serve machines, which perform final freezing and aeration. The machines contain a freezing cylinder surrounded by a refrigerant coil. The mix is pulled from the refrigerated hopper into the freezing barrel using an auger system. As the auger rotates, it scrapes the interior barrel surface and simultaneously compresses the mix forward while incorporating air. Air is introduced through a calibrated orifice that meters flow based on pump rate. The ratio of air to mix is tightly controlled to produce the desired overrun, which is typically between 30 and 45%. This ensures a light texture without exceeding melt resistance limits. As the mixture moves through the freezing barrel, it begins to crystallize along the interior surface. Scraper blades continuously remove frozen product and fold it into the flowing stream. The barrel is chilled using a sealed system filled with R404A or similar food-grade refrigerant. The expansion valve regulates evaporator pressure to maintain a barrel wall temperature near -10 degrees Celsius. The partially frozen soft serve exits the cylinder at a semi-solid state with uniform aeration and consistent temperature. The product is dispensed directly from the extrusion nozzle into cones or cups using a gravity-fed or pump-assisted mechanism. Flow rate is controlled by a handle-actuated valve that opens a piston or gate at the nozzle outlet. The nozzle is shaped to produce the distinctive swirl pattern through laminar flow and rotational motion. The final product has a temperature near -6 degrees Celsius and maintains this state for several minutes under normal ambient conditions. No post-processing or hardening occurs after extrusion. Flavor variations are achieved through pre-flavored base mixes or inline syrup dosing. For syrups, a separate pump introduces concentrated flavor into the liquid stream before freezing. Syrup flow is matched to mix rate using flow meters and feedback control. Chocolate-dipped variants are produced by inverting the cone into a vat of liquid coating held at a fixed temperature. The coating solidifies upon contact with the cold, soft-serve surface. The solid layer forms within 2 seconds due to the sharp temperature gradient and the high coconut oil content in the coating formula. Multi-flavor twist products are created using a dual-cylinder system. Each freezing barrel processes a different flavor. Both barrels feed a common extrusion head that contains two internal chambers. A Y-shaped nozzle merges the two flows at the outlet while maintaining separation. The twist effect is generated by the natural helical movement during downward extrusion. Inclusion-based variants such as candy or cookie pieces are added manually at the serving point. Toppings are not incorporated during freezing as they would interfere with scraper operation and pump integrity. Specialty formats such as Blizzard products use the same base soft serve dispensed into mixing cups. Solid inclusions are added from bulk hoppers and mixed using a vertical blender with a custom blade. The mixer agitates the entire volume briefly and evenly distributes solid inclusions without altering temperature or structure. The mix used for Dairy Queen soft serve has a fat content near 5% and milk solids non-fat between 11 and 12%. Stabilizers control ice crystal growth during freezing and maintain uniform viscosity during storage. Emulsifiers assist in fat dispersion and reduce weighing during freezing. Overrun is mechanically induced by synchronized air injection and auger transport. Storage tanks are cleaned with automated CIP cycles between production runs. Freezing cylinders are cleaned manually or with clean-in-place systems depending on model configuration. Syrup dosing systems are flushed with warm water after each flavor change. Coating vats are reheated and filtered periodically to maintain viscosity and clarity. All equipment involved in Dairy Queen production is constructed from stainless steel with hygienic welds and polished surfaces. Flow paths are sealed using tri-clamp fittings and silicone gaskets. Pumps use sanitary diaphragms or lobe rotors for gentle handling. Freezing units are maintained at fixed compressor settings based on product load and ambient conditions. The mechanical structure of the soft serve is defined entirely by air cell dispersion, fat matrix stability, and ice crystal size. Each parameter is determined by process inputs such as homogenization pressure, barrel residence time, and freezing surface temperature. No component of the product is batch frozen or aged at the point of service. Every portion is frozen continuously on demand and delivered immediately for consumption. Structural integrity is preserved through shear-controlled mixing and precise overrun regulation. Nestlé ice cream production begins with bulk ingredient staging in temperature-controlled storage silos. Whole milk is held at 4 degrees Celsius in insulated stainless steel tanks fitted with agitators to prevent separation. Cream is stored separately in jacketed vessels and maintained at a consistent viscosity for accurate metering. Granulated sugar is housed in dry ingredient silos connected to the batching system via enclosed auger conveyors. Formulation is initiated by transferring milk and cream to the primary blending tank using positive displacement pumps with flow meters. The tank is jacketed and equipped with high shear agitators that disperse solids efficiently into the liquid phase. Sugar is dispensed from the silo using screw feeders that meter flow by weight. Dry milk solids are pulled into the tank through a Venturi adductor mounted on a recirculation loop. Stabilizers including guar gum and carrageenan are introduced as dry powders via a sealed hopper with rotary valve discharge. Once all components are loaded, the mix is agitated at low speed while steam is applied to the tank jacket to raise temperature to approximately 65 degrees Celsius. This step ensures solubilization of dry materials and begins the hydration of stabilizing agents. When the target temperature and viscosity are achieved, the mix is routed to the pasteurization system through a network of sanitary process piping. Pasteurization is carried out in a plate heat exchanger that subjects the mix to a thermal profile reaching 83 degrees Celsius. Holding occurs in a tubular section sized for 30 seconds residence time at peak temperature. The mix is then immediately cooled to 4 degrees Celsius using a countercurrent flow of chilled water or glycol solution. The cooled mix is sent to a set of aging tanks for further stabilization. Aging tanks are vertical silos fitted with slow-speed agitators to maintain uniformity without air incorporation. Mix resides in the tanks for a minimum of 4 hours and often up to 24 hours, depending on product formulation. During aging, the fat crystals begin to nucleate and proteins reach full hydration, which contributes to improved, overrun, and final texture. Before freezing, the aged mix is pumped through a high-pressure homogenizer that operates in 2 stages. The first stage uses a narrow orifice under 2,000 pounds per square inch to break fat globules into submicron particles. The second stage at reduced pressure eliminates aggregates to produce a fully dispersed emulsion. Homogenization ensures improved creaminess and resistance to fat separation during storage. Flavoring is performed in-line immediately before freezing using precision metering pumps. Flavor oils, cocoa solutions, coffee concentrates, and fruit essences are introduced via multiple injection ports into the flow stream. Flow sensors and control valves maintain exact volumetric dosing. Color additives are similarly introduced where required for specific variants. The flavored mix enters a continuous freezer, which consists of a horizontal, scraped surface heat exchanger. The interior barrel is cooled externally by a closed-loop ammonia system that maintains wall temperature below -25 degrees Celsius. The barrel is fitted with a rotating dasher that scrapes frozen product off the wall while mixing it with incoming liquid. Air is injected through a calibrated orifice located near the inlet, which determines the level of overrun. Overrun in Nestlé ice cream is typically maintained between 40% and 60% depending on the product line. The level of air is controlled by adjusting air pressure, dasher speed, and mix feed rate. Low overrun varieties are set below 40% for premium texture, while novelty products may be aerated to a higher extent for volume efficiency. As freezing proceeds, the product reaches a semi-solid state and exits the freezer through a pump that delivers it to the ingredient blending system. Solid inclusions, such as chocolate chunks, cookie dough pieces, fruit particulates, or caramel bits, are stored in hoppers above the blender. Each inclusion is gravity-fed into a feed auger that meters pieces into the ice cream stream in real time. The blending unit incorporates the inclusions into the flow path using horizontal paddles that avoid crushing fragile components. The feed rate of inclusions is electronically synchronized with the freezer output to maintain uniform distribution. Inclusion size and moisture content are tightly controlled to ensure structural integrity and to prevent bleeding or hardening after freezing. Products that require variegates such as chocolate fudge, caramel, or fruit syrup receive them at a second manifold downstream of the inclusion blender. A peristaltic pump draws variegate from a chilled tank and injects it through a fixed nozzle into the center of the ice cream flow. The pipe downstream is segmented to create controlled turbulence that folds the variegate through the product without mixing it completely. Once all ingredients are combined, the product moves to the filling station through a flexible insulated hose. Depending on the format, the product is filled into cups, tubs, cones, or novelty molds using piston fillers or rotary valves. For cups and tubs, the ice cream is deposited directly into pre-formed containers lined up on an indexing conveyor. Fill volume is precisely managed through a servo-controlled drive connected to the piston stroke length. After filling, surface leveling is performed by mechanical scrapers or rotating wipers depending on the container geometry. Some formats receive additional toppings such as syrup drizzles or solid garnish, which are deposited using vibratory trays or robotic arms. The containers then proceed to the lidding station, where lids are applied using pneumatic cylinders and heat or pressure sealing mechanisms. Filled and sealed units are then transferred into the hardening tunnel, which is a spiral or straight line blast freezer maintained at -35 degrees Celsius or lower. The air velocity within the tunnel is controlled by multiple high-speed fans and directed across the containers in a cross-flow pattern. Residence time in the hardening tunnel varies between 30 minutes and 3 hours, depending on product size and thermal load. During hardening, the unfrozen water content solidifies completely, and the overrun structure becomes locked in place. Ice crystal growth is minimized by rapid freezing, which prevents graininess and ensures smooth texture. Hardening is considered complete when core temperature of the product reaches below -18 degrees Celsius. Once hardened, products are ejected from the tunnel and conveyed to the packaging line. For multi-pack items, individual units are collected into groups by mechanical diverters and placed into cartons by robotic pick-and-place systems. Cartons are formed from flat blanks using hot melt glue and folded by rotary formers. Cartons are coated with batch information using thermal inkjet printers. Carton product proceeds to case packing, where cartons are loaded into corrugated cases using side-load or top-load machines. Cases are sealed using tape or glue and labeled with destination and tracking codes. Finished cases are conveyed to automated palletizing stations, where they are stacked using articulated robotic arms onto wood or plastic pallets. Pallet patterns are selected by software based on carton size and unit weight to maximize stability and airflow in cold storage. Stacked pallets are shrink-wrapped with polyethylene film and transferred to blast freezers for holding before distribution. Final storage temperature is maintained at -28 degrees Celsius to -30 degrees Celsius with continuous airflow to prevent warm zones. The entire process from raw ingredient batching to final frozen storage is controlled by distributed PLC systems that communicate over industrial Ethernet. Parameters such as flow rate, temperature, pressure, inclusion count, overrun, and fill weight are monitored in real time. Feedback loops allow self-correction of dosing systems and line speed synchronization. No manual handling occurs at any stage after ingredient delivery. Ingredient silos, mix tanks, pasteurizers, homogenizers, freezers, blenders, fillers, tunnels, conveyors, and packers are all enclosed and automated. Cleaning is performed using clean-in-place systems that circulate caustic, acid, and rinse water through the entire process loop. Each product specification includes parameters for viscosity, Brix value, fat content, solids non-fat, pH, overrun, inclusion percentage, swirl concentration, core temperature, and packaging weight. All values are logged per batch and validated against product standards before release. Nestlé ice cream is defined by tightly regulated thermal transitions, physical dispersion of fat and air, inclusion integrity, and packaging precision. The resulting product has a defined melt curve, scoop resistance, and storage life, which are engineered through material control and mechanical process sequencing. No process stage is isolated or batch dependent beyond the initial mix. All subsequent steps are flow-through and occur under continuous conditions to allow high throughput with minimal variation. Formulation changes are implemented by adjusting source tank routing and modifying pump set points. Multiple product lines operate in parallel using shared infrastructure with staggered schedules and automated changeovers. Flavor switching involves purging lines with heated water, followed by air blows and conductance verification before the next product introduction. Nestlé's frozen dessert output relies entirely on integration between thermodynamics, fluid mechanics, solids handling, and process control. Every movement and phase change contributes to the structural and sensory properties of the final package. Nerds begin as a hot, clear sugar melt that is deliberately forced into a brittle glass because the final candy is defined by controlled fracture rather than molding. The line starts by preparing a sugar solution that can be concentrated without seeding unwanted crystals. Granulated sugar is screened to remove clumps and to tighten the crystal size range. Fines are limited because they dissolve too fast and can caramelize at hot surfaces. Water is filtered and tempered so dissolution conditions stay repeatable. Corn syrup is held in jacketed tanks to keep viscosity stable for metering. Acid powders, salts, flavors, and colors are staged in separate feeders because nerds often run multiple flavors in parallel. Sugar and water enter a dissolver with strong agitation. The goal is a fully dissolved solution with no grain residue. Any undissolved grain becomes a nucleation site that can trigger premature crystallization. The solution passes through strainers to remove stray solids and then feeds a continuous cooker. In the cooker, the syrup is heated rapidly to drive off water and raise solids to the level needed for a hard candy glass. Many systems heat under pressure so temperature can rise above the normal boiling point without flashing. That allows fast heat transfer and short residence time. The syrup then enters a flash stage where pressure drops and water vapor leaves quickly. Flashing tightens final moisture and also cools the syrup slightly by evaporative loss. Final solids must land in a narrow window. Too wet and the sheet will bend and tear instead of shattering. Too dry and the sheet will explode into excessive dust when fractured. Corn syrup is injected as a crystallization control lever. It reduces uncontrolled graining and helps keep the candy glass consistent from run to run. Its metering is precise because it also changes brittleness and fracture behavior. After the final concentration step, the syrup is cooled through heat exchangers to a temperature that protects flavors and supports controlled casting viscosity. The process often splits into two streams at this stage to create two flavors and two colors for the paired pack format. Each stream receives its own acid and flavor additions. Acid is added after the hottest zones because high temperature and low pH accelerate sucrose inversion and can change texture. The acid is usually dosed as a solution to ensure fast dispersion. pH is controlled because it influences sourness and also influences how hygroscopic the finished candy will be. Flavors are injected late and mixed rapidly. Oil-based flavors are emulsified or carried so they disperse evenly. Color solutions are filtered and then metered into each stream. Uniform color matters because nerds are small and translucent and any streaking is visible. Static mixers fold the flow repeatedly to eliminate bands before casting. Casting turns the hot syrup into a thin sheet that can be fractured into granules. The syrup is deposited onto a cooled steel belt or onto trays as a continuous ribbon. Deposit rate and belt speed set thickness. Thickness is a key variable because it determines cooling rate and fracture size distribution. A thicker sheet cools slower and can retain internal stress. A thinner sheet cools fast and can become too brittle at the surface. Cooling is engineered to produce an amorphous glass with minimal crystal growth. Cooling plates under the belt pull heat out evenly. Air above the sheet is controlled so humidity does not condense, and so surface remains clean. Rapid cooling locks the syrup into a glassy state. If cooling is too slow, crystals can grow and the candy becomes gritty rather than sharp and crunchy. As the sheet cools, it can be conditioned to create predictable fracture behavior. Some lines flex the sheet slightly over rollers to introduce controlled microstresses. Others lightly score the surface to create preferred break paths. The aim is to reduce random oversized chunks and reduce the need for aggressive crushing later. The sheet must reach a brittleness that breaks cleanly under compression rather than smearing. Once the sheet is brittle, it is released from the belt and fed into a primary breaker. The primary breaker uses toothed rollers or oscillating bars to crack the sheet into chips. This first break is staged to avoid shattering into dust. Chips then feed a secondary reduction stage, often roll crushers, that bring pieces down toward the final nerd size range. Roll crushers are used because they apply compressive force and yield angular fragments rather than rounded beads. Crusher gap is the main size control. A smaller gap yields more fines and a narrower top size. A larger gap yields more oversize that must be recirculated. Feed rate must be steady because surges cause inconsistent reduction and more dust. Roll speed and surface texture also matter because they control how the chip is gripped and fractured. The goal is irregular pieces with sharp facets but limited powder. After crushing, the material enters screening. Vibratory screen decks separate by size in multiple fractions. The target fraction continues as product. Oversize is returned to the crusher for another pass. Fines are removed because they clump easily and create dusty packs. Fines can be used as controlled recycle seed in some systems, but only in small ratios because they raise cohesion and reduce free flow. Because nerds often come in two distinct colors, each stream is processed separately through crushing and screening. This keeps recycle loops color pure and prevents shade drift. It also allows each stream to be tuned for its own brittleness because acid and flavor loads can shift glass strength. If one flavor tends to shatter more, the crusher gap can be opened slightly for that stream while keeping the other tighter. Conditioning follows sizing. Even though the candy is glassy, it can hold slight moisture gradients from casting and cooling. Conditioning allows moisture to equalize inside each granule. This stabilizes crunch and reduces caking risk. Conditioning bins use controlled dry air so the product does not absorb humidity. Humidity control is critical because hard candy surfaces can become tacky when water activity rises. Tack leads to clumping and also to color transfer between pieces. A light finishing step can be applied to improve flow. Anti-caking agents can be dusted at very low levels in a tumbler. The purpose is to reduce surface adhesion points and to improve hopper flow. Application must be uniform because local over-application changes mouthfeel and creates visible dust. After tumbling, the product can be aspirated lightly to remove excess loose powder. For versions that emphasize a stronger sour burst, some sourness can be placed at the surface rather than only in the body. This is done by misting a very small amount of binder and then applying an acid sugar blend. The binder must be extremely light so it does not dissolve the glass surface. The acid blend adheres, and then the product is dried quickly to set. This creates a fast sour hit at the tongue because surface acids dissolve first. If the product format requires blending the two flavors, blending is performed after each stream has been sized and conditioned. Gravimetric feeders meter each color stream into a blender at the target ratio. The blender uses gentle paddles so it mixes without grinding. Over-mixing would generate fines by abrasion. The blending time is therefore short, and the geometry is chosen to fold the streams rather than shear them. Before packaging, the blended product is screened again to remove any fragments created in blending and conveying. This final screen improves pack cleanliness and improves weigher accuracy. Metal detection can be placed at this stage because product flow is stable and pieces are dry. Packaging begins with controlled feeding into weighers. Multi-head weighers are common because they can combine multiple small hopper dumps to reach target weight quickly. Consistent flow into the weigher depends on low fines and low humidity. Hopper walls are steep and surfaces are low friction. Vibration is used sparingly because vibration can create abrasion dust. For bag formats, the weighed portion drops into a vertical form fill-seal machine. Film is formed into a tube and sealed longitudinally. The portion drops through a funnel and settles. Transverse seals close the bag above and below the portion. Seal timing must keep granules away from the seal jaws. Dust management is important because sugar dust in the seal area can weaken the seal. Oreos are manufactured by producing a cocoa cookie wafer with a controlled snap and surface texture, producing a fat-based creme that holds shape without refrigeration, then assembling two wafers around a measured cream deposit before packaging to protect crispness. The cookie wafer begins with flour and cocoa handling because particle size and moisture define dough behavior. Flour is sieved to remove lumps and to aerate it for consistent hydration. Cocoa powder is sifted because it compacts and forms clods that create dark streaks. Sugar is screened to control crystal size and reduce dust. Leavening and salt are weighed precisely because they drive spread and porosity. Fats are tempered to a plastic consistency so they cream evenly and do not separate during mixing. Water is tempered because dough temperature controls sheeting and bake spread. Mixing starts by building a fat-sugar phase that controls texture. Fat and sugar enter a mixer and are creamed until sugar crystals are uniformly wetted and small air cells are incorporated. Air incorporation is controlled because it influences wafer porosity and snap. Too much air yields fragile wafers that crumble during sandwiching. Too little air yields dense wafers that lack the intended crisp bite. Salt and leavening can be added during creaming so they disperse evenly through the fat phase. Water is introduced next in a controlled stream. The water level is set to produce a dough that sheets cleanly without sticking. Water also activates leavening and hydrates flour. Cocoa powder and flour enter after water, so they are hydrated evenly. Mixing energy is reduced during flour addition to limit gluten development. Excess gluten makes wafers tough and increases shrink during baking. The endpoint is a cohesive dough that is uniform in color with no dry pockets. The dough is then conditioned for forming. Conditioning allows moisture to distribute and lets the dough relax so it does not snap back after sheeting. Dough temperature is held in a narrow band. Warm dough becomes sticky and smears on rollers. Cold dough cracks and produces rough edges. The line uses controlled dwell time and jacketed hoppers to maintain stable dough temperature. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through a series of reduction rollers that gradually thin it. Multiple reduction stages prevent tearing and keep texture uniform. Gauge rollers set the final thickness tightly because thickness controls bake time and final snap. Surface flour dusting can be used sparingly to prevent sticking. Excess dusting is avoided because it burns and creates specks. The sheet enters rotary cutting and embossing. Rotary cutters punch round wafers from the sheet while an embossed pattern is pressed into the surface. The embossing is functional. It controls thickness uniformity, adds texture, and influences how creme bonds. Docking holes are also created during this step. Docking vents steam during baking and prevents blistering. The sheet scrap around the cutouts is lifted and recycled back into the dough stream under controlled ratios. Scrap ratio is limited because repeated working increases gluten and changes dough rheology. Cut wafers transfer to an oven band and enter a tunnel oven. Baking is zoned to set structure and drive moisture to a low endpoint. Early zones melt fat and allow the dough to expand slightly as leavening gases form. Starch gelatinizes and protein set, turning the dough into a porous solid. Mid-zones develop color and drive off moisture. Later zones finish drying so the wafer becomes crisp and stable. Moisture endpoint is critical. If moisture is too high, wafers soften in the package and the sandwich loses snap. If moisture is too low, wafers become brittle and crack during assembly. Oven temperature and airflow are tuned to reach a narrow moisture band. Airflow affects surface drying and color. Strong airflow dries faster and can increase snap. Lower airflow yields a gentler bake and can retain a softer bite. The line controls top and bottom heat to prevent warping and ensure even bake across the wafer. After baking, wafers exit hot and fragile. Cooling stabilizes structure as fats resolidify and moisture equilibrates. Cooling conveyors use controlled airflow. Dehumidified air is often used because crisp wafers can absorb moisture from humid air. Cooling brings wafers to a temperature suitable for creme application. Wafers that are too warm will soften the creme on contact and can cause slip. Wafers that are too cool can be brittle and prone to edge chips. Wafers are sorted and oriented for assembly. Vision systems can reject misshapen wafers and cracked wafers. Thickness checks and color checks verify the oven profile. Good wafers are aligned in lanes, so the embossed side faces the correct direction. Alignment is important because the pattern must be consistent on the outside of the sandwich. Cream. Manufacture runs as a separate stream because it is a fat-based system that must remain stable and non-gritty. The cream is built from sugar, fat, and emulsifiers plus flavor. Sugar is milled or selected to a fine particle size so the cream feels smooth. The fat base is prepared from vegetable fats that are melted and then cooled to a specific plastic state. Plastic state matters because it determines how the cream whips and how it holds shape. Cream mixing begins by blending fat and fine sugar under shear. The mixture transitions from dry and crumbly to smooth as fat coats sugar particles. Emulsifiers are added to reduce viscosity and improve spread. Flavor is added late, so it remains strong. The cream is mixed until particle wetting is complete and the texture is uniform. Air can be incorporated in a controlled way to adjust density. Higher aeration yields a lighter cream that compresses easily. Lower aeration yields a denser cream with firmer bite. Temperature control in the creme is critical. If the creme is too warm, it becomes too fluid and can squeeze out during sandwiching. If it is too cold, it becomes stiff and can crack or fail to adhere. The process holds creme in a narrow temperature range where it is depositable and retains sharp edges after deposition. Cream is delivered to the assembly line through heated or conditioned piping. The depositor meters a precise mass onto each wafer. Depositing is typically done as a spiral or star pattern. The pattern controls spread when the top wafer is applied. The deposit height determines final sandwich thickness. Weight control is tight because it affects bite and package count weight. As soon as cream is deposited, a second wafer is placed on top. Placement systems pick wafers and align them over the cream deposit. The wafers are pressed together with a controlled compression. Compression spreads the cream to the edge without breaking the wafer. Too much compression crushes wafers and causes overspread. Too little compression leaves a tall deposit and weak adhesion. Compression also sets the final wafer to creme contact, which controls stability during transport. After sandwiching, the cookies move through a short setting conveyor. During this stage, the creme fat network stabilizes and holds the sandwich geometry. Cooling can be applied to firm the cream slightly. The goal is a sandwich that can be handled and packed without creme smear. The product is then inspected. Vision checks can detect misaligned wafers and missing cream. Rejects are removed automatically. Packaging is designed to protect wafers from humidity and to protect sandwiches from breakage. Sandwich cookies are stacked into columns and placed into trays. Trays hold stacks in position and reduce movement that would chip edges. The tray is then sealed inside a moisture barrier film. Film barrier performance is critical because wafer crispness depends on low moisture pickup over time. Stacking is controlled, so columns are uniform height. Uniform columns prevent uneven pressure that can break wafers. The stacking system uses lanes and pushers that align cookies without scuffing. Crumb control is important because crumbs in seal areas can compromise seal integrity. The line uses crumb extraction near tray loading and near sealing stations. The tray and film system passes through a heat seal station where the film is sealed to the tray. Seal temperature and dwell are tuned to create a continuous seal without warping the tray. Leaks allow moisture ingress, which softens wafers. Sealed trays are coated and checked by vision. Check weighers confirm pack weight. Sealed trays are then inserted into outer cartons. Cartons are erected and loaded with trays. Cartons add stacking strength and protect the film from puncture. Cartons are closed and glued. Finished cartons are case-packed and palletized. Snickers starts as 3 independent streams that only meet at the assembly belt because nougat, caramel, and chocolate each require different heat histories and different flow behavior to stay consistent at scale. The nougat stream is built around controlled aeration. Sugar and glucose syrup are metered into a cooker and concentrated to a target solids level that will support a stable foam once mixed. The cook profile is kept short because long high heat residence darkens sugars and shifts viscosity. The syrup exits the hottest zone and is conditioned to a temperature where it can strengthen a protein foam without scorching it. In parallel, a foaming phase is prepared as a protein solution that can hold fine bubbles. The solution enters a continuous aerator where airflow and shear are controlled to generate a narrow, bubble-sized distribution. Density is measured continuously because density drives bar weight and final bite. If density drifts, the bar becomes heavy and tight. If density drops too far, the nougat becomes fragile and can collapse during cutting. The hot syrup and the foam meet in a continuous mixer designed to fold rather than whip. Folding distributes syrup through the foam while preserving bubble walls. The syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be dosed in small amounts to stabilize the air-fat sugar system and to keep the nougat smooth as it cools. Once the nougat reaches specification, it is deposited as a continuous slab onto a moving belt. A spreader head lays down a uniform band, and gauge rollers set thickness. Thickness control matters because it defines the core cross-section and the later chocolate ratio. The slab enters a cooling tunnel with staged zones that remove heat gradually. Gradual cooling prevents a hard surface skin forming over a warm interior because that skin can crack when the slab is bent or cut. While nougat is being formed, a caramel stream is cooked in parallel. Caramel starts as sugar and glucose, syrup combined with dairy components. The cook concentrates the mix to a solids endpoint that yields elasticity rather than glassiness. If solids are too low, the caramel flows and smears on knives. If solids are too high, the caramel fractures and creates sharp cracks under the chocolate coat. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it remains depositable and stable. Caramel is held in jacketed tanks with gentle agitation to prevent a surface skin. It is delivered to a depositor through heated lines that keep viscosity constant. The depositor is designed to lay down an even sheet rather than a rope. An even sheet is important because Snickers requires predictable bite across the full width of the bar. Peanuts are handled as their own stream because their size and dryness control both crunch and line stability. Roasted peanuts are screened to remove fines and broken fragments that would create dust and weak points. The nut size band is chosen to give a consistent surface coverage without tall peaks. Peaks can pierce the chocolate curtain and create thin spots. Peanuts are cooled after roasting, so residual heat does not soften caramel and does not melt chocolate during enrobing. Assembly begins when the cooled nougat slab reaches the layering station. Caramel is deposited onto the nougat as a continuous layer with a controlled thickness. A leveling bar spreads the caramel and smooths the surface. The temperature of both layers is managed closely. The nougat surface must be firm enough to support caramel without compression. The caramel must be warm enough to bond without sinking into the nougat. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the width with a calibrated feed rate. The nuts land on caramel while it is still tacky, so they adhere. A light compression stage can press nuts into the caramel to improve lock-in. Compression is tuned, so it increases contact without crushing nuts into fragments. The layered slab then enters a conditioning zone. This zone firms the caramel enough for clean cutting and locks nut position. Conditioning is staged to avoid large thermal gradients between nougat and caramel. Large gradients cause differential contraction and can create separation lines. The goal is a slab that behaves as one piece under knives. Edge trimming follows because slab edges often vary in thickness. Rotary knives remove edges and send trim to controlled rework streams. The main slab is then cut into lanes. Lane knives create long ropes of constant width. A crosscutter then cuts the lanes into bar lengths. Knife timing is synchronized with belt speed to maintain tight weight control. Knife surfaces and temperatures are managed because caramel can stick and smear if the blade is too warm or too cold. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between adjacent bars. Transfer points minimize drop height because impact can dislodge nuts and can dent the nougat. A brief pre-chill can be used to firm the bar surfaces. Firmer surfaces improve chocolate coverage and reduce nut movement during curtain contact. Chocolate coating is prepared in a separate system where temper is the critical parameter. Chocolate is melted and filtered to remove unmelted particles. It is tempered in a continuous tempering unit that heats and cools in stages. The process builds stable seed crystals and then sets a working temperature that keeps viscosity steady. Viscosity matters because it defines curtain thickness and therefore coating weight. If viscosity drifts, the bars become heavy or exposed. Enrobing applies chocolate with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a bottoming roller or a bath section that lays a uniform base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the thickness at edges and the foot at the base. Air knife settings are tuned so they remove excess without exposing nuts at corners. If a top pattern is used, a stringer drizzles thin lines across the wet surface. The pattern must be applied while the base coat is still tacky enough to bond. The bars then enter the cooling tunnel immediately, so the coat sets without slumping. Cooling is staged to protect chocolate crystal structure and to prevent cracks around nut peaks. The first zone sets the surface quickly, so the coat holds shape and locks nuts in place. Subsequent zones cool more gradually, so stable crystals grow without stress. Tunnel humidity is controlled to prevent condensation because condensation can create bloom and surface haze. Bars exit at a temperature that supports wrapping without scuffing. During cooling, the internal layers also stabilize. Nougat firms as its fat phase crystallizes and its bubble. Walls become more rigid. Caramel reaches its final elasticity and stops flowing at the interface. The chocolate coat becomes a barrier that slows moisture exchange and protects texture. Inspection follows cooling because surface defects are easier to detect when the coat is fully set. Vision systems check for exposed edges and bald spots and heavy feet. Weight checks verify that cutter control and coating control are stable. Metal detection can be placed before wrapping. Defective bars are diverted to rework. Rework is managed carefully because tempered chocolate cannot be recycled directly into tempered streams without remelting and retempering. Wrapping begins with steady bar spacing into a flow wrapper. Film is formed around each bar and sealed with heat and pressure. Sealed well and temperature are tuned to create strong seals without shrinking film onto the chocolate. Film tension is controlled to prevent scuffing. Code printing is applied for traceability. Wrapped bars can be collated into multi-packs or cartons. Collation uses lanes and gating, so bars group without impact. Cartons are erected and loaded and closed. Finished units are case-packed and palletized. Case patterns reduce movement that can abrade wrappers and stress seals.